Hi, everybody. This is the second week of the Precal Semester 2 review class. This week, we're going to focus on roots, how roots are related to factors and x-intercepts, and how we can use roots to find out things about a graph or a table or about an equation, and how we can take roots and use them to write equations as well. So the first thing you need to remember is that there are real roots and then there are complex or imaginary roots, meaning if we were looking at a graph, they would not be a visible place where the graph is touching the x-axis, but it doesn't mean that they don't exist. So you learned that roots are the x-intercepts of a graph. That is true, but only real roots are found that way. The degree of the polynomial, which is your highest exponent, tells you how many roots or zeros it has, but they may not all be visible and therefore they're not all real. We're going to start just by looking at real roots. So if you look at this graph right here, it says this is f of x. What are all the real solutions when the function is equal to 0, meaning when it touches the x-axis? And if you look, you can see that there's one place where it touches the x-axis, another place, and another place. And we need to find those three values. Now, I will observe that this is a bounce right here. If you remember from Algebra 2, when we were studying polynomial graphs, if there's a bounce, that actually counts as a root or an x-intercept twice. But here they're just asking for unique solutions. So we're just going to pick the three visible spots. So I see that there is an x-intercept over here at -8. That's a solution. I see it crosses at the origin. That's a solution. And I see that it crosses at between 6 and 8, so we're going to say that's 7. And that would be a real solution. 7 happens twice, but you don't need to write it more than once when they're just asking us for all the real solutions. Okay, another thing you might be asked to do is to be given an equation, and they may ask you to round values of the zeros to the nearest hundredth. So if they're letting you round, then that means you can use a calculator. You could use the Inspire or you could use the Desmos calculator, and you're going to find approximate zeros, places where it crosses the x-axis, and that we're expecting that they would be decimals, especially because we see decimals in the polynomial. So I'm going to switch over to the Desmos screen, which would be right here, and I'm going to type in 0.5 x squared plus 5.1x plus 9. And I think you can see it's a quadratic, and there's only two places where it crosses the x-axis. That's the most it could have. And it gives us that one of those zeros or solutions is -7.93, and another one is -2.27. And those would be our two approximate zeros rounded to the nearest hundredth, which is what they asked us for. So I'm going to attempt to get us back to the screen that is supposed to be where I can, there we go, where I can see what our notes. All right, so now we're done with that section. You've got some problems like this, you've got some problems like this in that section. Now, another thing that we can do is take a graph and write a version, probably the simplest version, of a polynomial with those particular intercepts. So can you look at a graph's roots and identify a function that could be written just off recognizing the x-intercepts? Can you write potential factors based on those x-intercepts? Keeping in mind that the degree of the polynomial tells you how many roots there are, even if some of them aren't real and visible on the graph itself. So for example, this is a cubic. I see that this is crossing in 3 places. A cubic can only have 3 roots at most, and they're all visible here. So I know that everything that, all the factors that I would write for this polynomial using x will be solvable with real solutions. So don't forget that roots can be repeated twice if you see the graph bounce, and even 3 times if you see the graph wiggle. Remember that factors are written using the opposite sign. So if I see that there's an x-intercept or a root or a zero of -4, then the factor that contains that root will actually look like x plus 4. When I see a root of 0, I don't even need a parentheses for that factor. It'll just be a single x. And then I also see that it crosses the x-axis at 3. So as a factor, that would look like x minus 3. And we're just going to find the answer choice that contains these three pieces. They all have x's. They don't all have x plus 4s. This one doesn't and this one doesn't. And an x minus 3, not here, so it must be this one. All right, now let's look at a different one. If we look at this one, we see this is a even function because it begins and ends going the same direction. I see a root here and I see a root here. Now this has 3 turns in it. This is a quartic. So technically this should have 4 roots, but if you notice, this is a bounce and this is a bounce. So what that tells you is this root is a repeat, and also this root is a repeat, and that would add up to 4. So what I'm going to do to show that the bounce happens, or that repeat x value happens, this x value that's at -5 would look like this. It's going to be written twice, or you can just write it squared. And this root that's a +4 as a factor would be written as a -4. And to show that it bounces there as well, I'm also going to include a second power to show the repeat root. And that's it. That's all I have to do. Now, I am going to tell you that this is a downward facing quartic, so there should be a negative in front of that. An upward facing one would look like this. So you can also tell what the leading coefficient is if it's negative. If it's an even polynomial, which this is, it's a 4th power, but it's beginning and ending facing down, then that means it is a negative leading coefficient. Now in a table, you can find roots by looking for where the y value is 0. So here we have a function called f of x, and they're asking us to write the equation. It's quartic, so that means I'm looking for up to 4 roots, and I see clearly 4 different places where it crosses or touches the x-axis. So I'm just going to take those x values, -2, 2, 3, and 4, and write them as factors, which means I need to switch the signs, and that will be enough. Now it does say write this in standard form, so it actually wants me to multiply these together. I would multiply these together, which they actually are a difference of squares. When you multiply these together, and I'm just doing this fast in my head, and then you need to multiply these together to get something that has an x to the 4th power. So x to the 4th, this is a -7x cubed. I have an x squared times 12, so 12x squared and a -4x squared. Those will combine to be 8x squared. I have a -4 times -7x. I have a -4 times 12. And this would be my standard form answer. Multiplying all this together. If it asks for standard form, it doesn't want it left in factored form. This one said it could be left in any form, so that's why I did not feel the need to multiply those all together. So now we're going to take a little break, and it's going to feel like it's out of nowhere, but it does relate to roots. We need to remember how to simplify radicals, not just square roots, but even cube roots, things like that. How to change it into an exponential form, which we can do, and also when we have negatives inside the radical, how we handled those, because that's tied into complex roots. So if we have a cube root like we do here, I think the quickest thing to do to simplify is to raise all of these to a power, the power that's in with each thing. The 216 has an invisible first power, the x has a 7th power, the y has a 5th power. We can rewrite that in a fraction exponent or a rational exponent using the power on the inside on top and the root that's on the outside on bottom. So this would be 7/3 for the x exponent, and this would be 5/3 for the y. And anything that can be simplified should be. The only one of these that does actually simplify perfectly is 216 to the 1/3 power. What is the cube root of 216? And it's actually a whole 6. So this is the answer that we are looking for, and we should see that right here. Okay, these cannot be simplified because that 7 and that 5 are not divisible by 3. All right, what about a negative radical? So let's remember that we can always take a -1 out of any radical by bringing the letter I into the problem. And I'm sorry, this is not a negative anymore. This is a -1 times a 180. So now we just need to factor 180. Think of factors of 180. The biggest square, perfect square that I can think of is 36. 180 is 36 times 5. And we can take the square root of 36, which is 6. And so this becomes our most simplified radical form. You are going to have an imaginary root or imaginary number here if there was a negative in the radical. Okay, unless there's something that ends up canceling it out, and that does not happen here. Okay, so now that we remember that we can have negative square roots, then that's where we get to talking about the nature of roots. And the nature of roots just means, can you look at something and tell whether it's going to have real roots, complex roots, or perhaps both? Remember, the degree of a polynomial tells you how many roots it has. If they're all real and unequal, meaning they're all unique, then we'll see that the degree matches exactly the number of visible x-intercepts. If they're all real and equal, meaning we have a repeat root, then we'll see a bounce or a wiggle to show that repeating root. But if there's a turn in the graph above or below the x-axis, and it prevents a graph from coming back down or going back up and touching the x-axis, that signals the presence of some imaginary or complex roots. And remember, if we see that happen, imaginary roots come in pairs. So we're never just going to say there's one imaginary root. It's always going to be, they're always going to come in pairs. If it's a quadratic, of course, you can always use quadratic formula to find the nature of quadratic's roots. Remember, quadratic formula can show us by the discriminant value, the number that's inside the square root inside the quadratic formula. If it's negative, that shows you that there are imaginary or complex roots. So we're going to look at this quadratic that they gave us. It just says determine the nature of the roots. So we're going to take this a value, this b value, and this c value. You could graph this and see how many places it crosses the x-axis. If it crosses in in one place, that's at a whole number, or even a fraction that's perfect, like 1/2, or that has not a repeating decimal, that would be this example. If they're real and unequal, you're going to see them in two different places. If they're numbers that are reasonable, then we would choose this. If there's two places where they cross and they're unequal and they have decimals that go on and on forever and ever, we're going to choose this. And if we don't see it cross the x-axis at all, we can choose this. If you don't have a graphing calculator, then you also can answer this very quickly using the Pythagorean theorem, not the Pythagorean theorem, quadratic formula. And even more importantly, it's not even the whole thing. You just need to know what is inside that square root. If it's negative, you're going to choose this. If it's positive and a perfect square, you can choose this. If it's 0, you're going to choose this. And if it's some number that's not a perfect square, you're going to choose this. Okay, so I'm going to take negative 18b, square it, minus 4 times a times c. And that gives me 324 minus, this is 260, and that gives me 64. So what I have inside of a square root is a 64. Is that a perfect square? Yes. So it's not irrational. It's not imaginary. But what that means is if I take the rest of the quadratic formula, negative b plus or minus the square root of all that over 2 times a, is that going to give me two numbers that are exactly the same or two numbers that are different? That's the difference between equal and unequal. It would only be equal here if this was a 0, because 18 plus 0 divided by 2 and 18 minus 0 divided by 2 would give you the same answer. This is not a 0, this is an 8. So one solution is going to be 18 plus 8 divided by 2, and one of them is going to be 18 minus 8 divided by 2. That's going to be two real unequal rational solutions. If we look at this, this is a cubic. A cubic has 3 total roots. But if you look at this graph, I only see one real root. So that means there are 2 imaginary roots. Okay, so I need to find an equation that shows that it crosses, it has a factor that shows a crossing through negative 8. Remember, if the 0 or the root is negative, then the factor is going to be positive. So I don't want to choose this and I don't want to choose this. but I have two imaginary roots. So I need to make sure that the other part, these two choices, one of them would give me imaginary solutions. If I set this equal to 0, I'm going to get 4 and -4 as my solutions. Those are real. That's not what this is. This says they're imaginary. If I set this equal to 0 and solve it, I'm going to have a negative square root. I'm going to get two imaginary roots. It has to be this. Okay, now we're going to talk about powers of I. Remember that I is known as the square root of 1. So anytime you see the square root of -1, you can always replace that with an I squared would be this times itself, which would become just a -1 without the square root. I to the third would be taking this and multiplying it by another I. Well, that's going to give you -I. I to the fourth is taking this I to the third and multiplying it by another I. Well, that would give you -I squared, and -I squared is -1, which is +1. Any power above 4 is going to be one of those 4 values. It's either going to be I, -1, -I, or 1. I'm going to write that over here. I, -1, -I, and 1. This is I to the first power. This is I to the second. This is I to the third. And this is I to the fourth. So if you divide a power by 4, some random power like this, if it divides by 4 evenly, then it's this last answer, 1. But if it has a remainder of 1, we bump the answer up to this. If it has a remainder of 2, it bumps to this. If it has a remainder of 3, it bumps to this. So what I would do is look at this. Now this is 4 different imaginary numbers, all with different exponents. Now, you know that if you multiply things that have the same base together, you can add those exponents. So I'm going to add 15 and 15 and 27 and 8. What that's going to end up giving us is I to the power of 65. So all I'm really doing is simplifying this. Now, 65 does not divide by 4, so I know it's not going to be 1. But what I can do is divide 65 by 4 and see how much is left over. And if I do that, I end up with a remainder of 1. So that tells me that my answer is just I. And that's what I'm going to choose. Now, if you have a more complicated problem like this, this is not a multiplication problem. So I'm going to have to simplify this. I'm going to simplify this. I'm going to simplify this. And I'm going to simplify this and see if I can simplify those answers. So I to the 60th. 60 does divide perfectly by 4. So that means I get to use, 1. This gets replaced with a 1 because it is a perfect, the exponent is a perfect factor of, or multiple of 4. 112, does that divide by 4? I believe so. That would be a 2. That would be 32. That would be, it also divides perfectly by 4. So minus, and I'm going to replace this with a 1 plus. Now I have a 10 here, and I'm just trying to figure out what is I to the 93rd power going to reduce to. If I divide this by 4, I end up with a remainder of 1. So if I have a remainder of 1, I'm going to put an I in place of I to the 93rd power. And then I have -6 times I to the 36th power. 36 divides perfectly by 4. So I'm going to put a 1 there. And so I have 1 minus 1, which is 0. I have a 10i, and I have a -6. And I'm going to rewrite that in complex number form, which is always to put the real part first and the imaginary part second. So -6 went up to the front, plus 10i goes to the back, and that is my answer. So I can do any operations I want to with real numbers and imaginary numbers combined. So leading to that, we can do any of this. It says imaginary numbers can be added, subtracted, multiplied, or divided. Any power of I can and should be simplified. And if we ever have an answer with a fraction that has an I in the bottom, I have to rationalize that. And I'm hoping we'll have a chance to work on that, but we may not here. But just remember, we can't have that. So anything that I can simplify, I'm going to. The square root of 4 is 2. The square root of negative 36, well, 36 is 6, but I have to put an I out there because of that negative the negative in front of the radicand. Then I have minus square root of 49, that's 7, plus the square root of negative 49. So the negative is going to come out as an I, and the square root of 49 is 7. So this is going to be 7I. All I need to do now to have the answer fully simplified is to combine the real pieces, 2 minus 7, and combine the imaginary pieces, 6I and 7I added together would be 13I. And this is my answer in a complex number form. Now multiplying, this is one term times one term. You could simplify the radicals if you want first, or you can just multiply the real parts together and the imaginary or the radical parts together, and it takes care of itself because negative 1 times negative 4 is a positive 4. So this ends up just being 21 times 2, which is 42. It's not even imaginary. Now, complex numbers. Remember, complex numbers aren't just imaginary numbers. They have both real and imaginary components. We just treat them like terms. We can combine real pieces with real pieces and imaginary pieces with imaginary pieces when we're adding and subtracting. If we're multiplying, we can combine them with multiplication. Remember, just like I said above, if you have any powers of I that can be simplified, you should. And if you have any denominators containing I, then you need to rationalize them. So this problem is just a simple subtraction problem, negative 12 minus I, and then I'm going to distribute this minus sign to the 7, or the negative 7, which makes it positive, and I'm going to distribute this minus sign to the 2I. And so this is what I have. I'm going to combine the real pieces together, negative 12 plus 7, and I'm going to combine the two imaginary pieces by adding them together. That's a negative 1I and a negative 2I. That would give me negative 3I, and this is my complex number for my answer. I can multiply. It'll be just like using FOIL. Negative 1 times negative 7, negative 1 times 6I, 3I times negative 7, and 3I times 6I. And remember, I squared can always be simplified. So I'm going to combine these two. That's negative 8I. And I squared is the same thing as negative 1, so I can simplify that. And that actually turns out to be a real piece. So I'll combine the 7 and the negative 18, and I will put the imaginary part at the end, and that's my final answer in complex number form. We can always square, cube, raise to any power, and a complex number. Squared is just times itself. So I just have to do a simple FOIL problem here. Negative 2 times negative 2, which is 4. Negative 2 times I. Another negative 2 times I, and an I times an I, which is I squared. These two can be combined, so that would be a minus 4I. I squared can be reduced to negative 1, so my real part would be the 4 minus the 1, and my imaginary part would be the minus 4I. All right, now that we've been working with complex numbers a little bit, can we find roots of any quadratic? Remember, they could be real, but if the discriminant is negative using the quadratic formula, it's going to be a complex number, and we're going to reduce it to this form if possible. So remember, A is 1, B is negative 2, and C is 26 in this particular problem. So using quadratic formula, I'll do negative B plus or minus the square root of B squared minus 4 times A times C all over 2 times A, which would just be 2. So if I work on the discriminant, I get 4 minus, this ends up being 104. So I end up with 2 plus or minus the square root of negative 100 over 2. I can simplify that. The square root of negative 100 is 10I. So this is really 2 plus or minus 10I divided by 2. And then I can simplify that. 2 divided by 2 and 10I divided by 2 ends up being 1 plus or minus 5I. These are my two solutions, 1 plus 5I and 1 minus 5I. And we can do that even if the A value is not a 1. It just means we have to do a little bit more math, but we can do it. So negative B plus or minus the square root of B squared minus 4 times A times C over 2 times A. So if I simplify that, I get 64 minus, I should know this, and I have forgotten to write it down. We get 64 minus 204, which is negative 144 over 2 times 4, which is 8. So I can reduce the negative 144. Oh my, hold on. I'm about to lose my power. Just give me a second. Hope that I don't unplug the wrong one. And of course I did. I unplugged the wrong one. Okay. Give me 1 second. I have to get my connection back on, but I think I'm still in business. We're so close to being done. Okay. Here we go. Just take a second for it to warm up because I had it unplugged. There we go. Okay. So I can totally simplify this negative square root of negative 144. That would be 12i over 8. I can reduce this. 8 over 8 is negative, or negative 8 over 8 is negative 1. 12i over 8 reduces to 3/2 I, right? 12 over 8 reduces to 3 over 2. And this is my solution. You could also write 1.5i. That would be okay. If it's a decimal that's perfect like that, you could use that. I would keep it in the fraction form. So those are my two roots. Those are imaginary. If I went and looked at this graph, I would not see it crossing the x-axis at all because both of the roots are imaginary or complex, we could say. Okay, and the very last thing that we're going to review and do a couple practice problems on your homework is, if you're given roots, can you write the simplest quadratic equation that has those roots? If they're complex, you should also be able to do that. But I have over here a little cheat. Not a cheat, it's mathematically sound for how you can use those roots without putting them in factored form and having to do a lot of multiplication work. There's a quicker way to get that quadratic with those complex roots. I'll show you in a minute. First of all, if you have real roots like 4 and negative 6, you should very quickly be able to put those into factors and then multiply those factors together, and that's going to give you that quadratic equation set equal to 0 that it's asking for. So we'll do x squared plus 6x minus 4x minus 24, and that ends up simplifying to this, and that would be my answer for that one. Now, you can write, and we did this year in my math class. I said, okay, one of the roots is 9 plus 6i, and one of them is 9 minus 6i. Now, since they both started with a positive number, that's why they both start with a minus in the factored form. You can do this. You could distribute that minus sign to these and then do a very complicated multiplication problem. But there's actually a better way called the sum product method that will allow you to do this much faster. So what you're going to do is you're going to take the sum of those two roots, the positive version and the negative version. And when you add 6 plus I and 9 plus 6i and 9 minus 6i, you get a sum of 18. Okay, put that aside for a second, and then you're going to work on the product of those two roots, 9 plus 6i times 9 minus 6i. 9 times 9, 9 times negative 6i, 9 times positive 6i, and 6i times negative 6i. And when you do that work, I'm sorry, that's a plus. These cancel out, and you end up with 81 minus 36. I squared turns to negative 1, and this ends up being 81 plus 36, which is 117. So you have everything you need now to write the equation. You're going to assume that the a value is 1, because I said we're finding the simplest quadratic that would have these roots. And what you're going to do is your b value is going to be, your middle, this thing right here, is going to be by taking the opposite of the sum that you came up with and dividing by the a value of 1. So the opposite of 18 divided by 1 is negative 18. And then you're going to take the product that you got, 117, exactly the sign that it was, and divide it by your a value. So in this case, that is my c value. So my quadratic that has those two roots will look like this. It's the opposite of this sign and exactly this sign. This becomes my b value, the opposite of this. This becomes my c value, and we assume an a value of 1. And that is it for today, guys. We'll see you soon. Let me see if I can